Hey guys, today we are gonna do something fun. We are gonna dive into the world of cellular automata. If you're into computer programming, you must have heard of cellular automata or Conway's Game of Life. If you get Conway's Game of Life, you're even gonna see a demonstration of it running in the background. But Conway's Game of Life is not what we are going to do today, because quite honestly, I find it boring. Let me quickly explain what cellular automata is before jumping into what we are going to do today. If you already know about it or have attention span of a pigeon, you can find video segments in the description below. Cellular automata are sets of simple rules that are applied repeatedly to a grid of cells. Each cell can be in one of a finite number of states, and the state of each cell is determined by the state of its neighbors according to a set of rules. In Conway's Game of Life, the cells have either the state of 0 or 1, which are associated with being dead or alive respectively. The rules of the game are also very simple. For each cell, you add up its live neighbors. If the number of live neighbors for one cell is less than 2 or more than 3, that cell is going to die, otherwise it's gonna be alive. So in this example, the cell in the middle is going to remain dead because there are too many ones around it. Honestly, I would have died too if there was too many ones around me. Anyway, from these simple rules, it's possible to generate some funny looking stuff. According to Wikipedia, this is a glider gun, creating gliders. I mean, sure. But because of its simplicity in state and rules, the patterns emerging from it are very limited. That's what we are going to change today. So I came across this blog post the other day and I decided to implement some of the stuff mentioned there. So the basic idea is we take the normal Conway's Game of Life and we add shit like new state and new rules to it. So instead of just looking at each cell's immediate neighbors, we are going to look into a wide range of neighbors on different layers. So we are turning cellular automata into multiple neighborhood cellular automata, or MNCA for short. In theory, MNCA enables us to generate patterns that resemble biological systems such as cell dividing, or even more abstract concepts like flow of a fluid. That's how I think the game Noita is doing its fluid and fire spreading simulations. It's only my guess though, I don't know for sure. With that, multiple neighborhood cellular automata is what we are going to make today. Let's get to work. So I created a Unity project, and as a first step, I decided to just show a random grid on the screen, and then I decided to implement the Conway's Game of Life. As you can see, I made a couple of bugs along the way, but those bugs were pretty easy to fix, so after a couple of attempts, I had Conway's Game of Life running. I decided to scale up the simulation even more to see what happens, and what happened was not good.
Oh shit, not good.
My PC was basically choking on the number of cells that it was simulating, which is not a good sign when you have a very basic simulation running. And there you go, this is 1 million cells running Conway's Game of Life at a whopping 2 seconds per frame. You heard that right. Now the reason it's performing so poorly is because I created a new game object for each cell and I didn't have to do that. So I'm going to change this implementation to something better. The idea is, instead of having one object for each cell, we can have one texture and just display everything on that texture. So I made the changes and boom, everything got worse. At this point, the only thing that comes to mind is just optimizing the code, and I did that, and this is the best result that I got. So as you can see, the simulation is taking 35 milliseconds and visualization is taking 150 milliseconds on each frame. As a reference, if you want your game to run at 60 frames per second, you only have 16 milliseconds to run everything. And those of you who are good at math, we'll know that 35 plus 150 is way bigger than 16, like way bigger than 16. So you might think all is lost. We cannot even run Conway's Game of Life efficiently. How can we ever run Multiple Neighbourhood Cellular Automata? And here comes to the rescue. Compute shaders. So I scrapped and redid everything in compute shaders, and here's the result. Oops. Okay, fix the bug, and wow. Look how smooth it is. I don't know how good it will look on the video, but it is so good. Holy shit. Here I have zoomed in a little so you have a better idea of what's happening. At this point we are ready to switch to MNCA and we have a lot of performance headroom. For reference, the Conway's Game of Life was running at 300 to 400 frames per second, so we are gonna be good. The first form of MNCA that I tried making was just taking Conway's Game of Life and we increased the number of neighbors that we take into account. In this simulation we are taking 121 neighbors and we are adding their values up. This simulation is called bugs, and you can probably see why it's called that. However, I feel like the simulation is a little bit empty. So let's try to adjust some parameters. I think I've gone a little bit too far. I think this is much better. And you can also see some new patterns emerging. It's like a star or something, I don't know. Anyway, let's move on to the next experiment. This one is a little bit different. So instead of taking one set of neighbors, like for example a set of 8 neighbors, we are gonna take 2 sets of neighbors with different shapes. This should allow some complex behavior to emerge. In this simulation we are combining a ring of neighbors with a circle of neighbors. And as you can see, the result looks pretty much like bacteria. Honestly, with this one I don't know what the fuck I did, it just looked cool so I put it here. Here you can clearly see cell dividing happening. In this one I gathered neighbors in a plus formation, and as you can see it promotes straight lines. I also tried some configurations with diagonal lines, but these are not exciting. Now if you go back to the bacteria simulation, something here is bothering me. To put it elegantly, this looks like shit. It's so jiggly and pixely, with all due respect to pixel and voxel art games of course. But what I'm gonna try to do is try to smooth some things out. As I was trying to smooth it out, I had a very interesting bug. Everything had a tint of blue, which gave me the idea of it might be better if you also color those cells. I don't know exactly how, but we get there. Now look at this majestic view, it's so much better. Now this one is very interesting. For some reason it gives me existential dread. Okay, now let's talk about coloring. One simple way you could do coloring is by having different species and then assign a different color to each one of those species. But I'm not a simpleton, I'm a sophisticated person. So naturally, I have to make things complicated. And now I have to explain it with my shitty editing skills. Watch me try. One way to do coloring is to have a color palette and choose a color from that based on a parameter between 0 and 1. But that would be simple, and remember, no simple. So what do? We add more color palettes. And then we use the merge function to merge all those color values into one single value. Here's a list of merge functions that we are going to use. You might have seen these names in Photoshop. They do the exact same thing here. And here's a list of parameters that we use to choose a color from those color palettes. And after 2 weeks of work and experimenting with colors, here are the results. Anyway, that's all I had for this video. If you liked it, please like, subscribe. If you didn't like it, don't subscribe, or dislike, I don't know. And I see you guys in the next video.